Okay, and welcome to the first talk of the year. And I am extremely pleased to introduce Professor Amindavar, who's visiting us from Tehran, Amirkabir University of Technology in Tehran. And he's been here for about most of the fall quarter and will be departing soon. And it's been a great pleasure for me because Hamid received his MS in 1987 from our department. He did work in optics and signal processing, and then he moved over to do some work in radar detection and signal processing and received his PhD in 1991 from UWEE. And since that time, he's been at Amirkabir, and he's a full professor of electrical engineering. So Hamid's going to talk about some interesting applications of volatility modeling, which is quite common in finance, to problems in electrical engineering, especially target tracking. So, Hamid?
Okay, thank you very much, Jim. Thank you very much for every one of you coming here today. I'm going to talk about a branch of science called GARCH, Generalized Autoregressive Conditional Heteroscedasticity. Its roots are in economy about 20 years ago, but gradually moved into more engineering applications, such as what we are going to discuss today very briefly. The persons that were involved in this project, or two projects, were Sayyid Hamid Fouladi, Muhammad Ihsan, Ramazan Ali, Maryam, Amir Mazdaqani, Professor James Ritzi, Professor Peyman Arabshahi, and me, Hamidreza Amindavar. What GARCH is a modeling, as I just mentioned. GARCH is an acronym for Generalized Autoregressive Conditional Heteroscedasticity. It means that if we have some signal, such as one that you see in here, yn, could be speech, could be any kind of signals. It could have some time-varying mean, and some modeling error. That modeling error is always a point that many people would like to work on. And the novelty that Professor Engel and Professor Bullerslev did about 20 years ago, or maybe more, was that they assumed that this noise is modeled as what you see in here, where it is comprised of another stochastic process called eta and another stochastic process, h of n, which h of n is modeled according to the equation below, which is called conditional volatility or time-varying variance. If I like to introduce you more to GARCH, we can think that GARCH processes are processes that a stochastic process whose variance follows an RMA process. So what you see here is an RMA process of order Q and P in general. So the attempts in GARCH modeling is to obtain the parameters that you see in here, alpha and betas, and also the parameters that might be involved in mu. Now, if mu is zero mean, then we are left with a simpler equation, as you could see in here, which is more amenable to discussions. If we assume the past informations are in here and called it a function such as psi, then the observation up to time n-1, given the past observations, is assumed to follow a normal Gaussian process whose variance is modeled by the volatility, which has the following form. So an application. of what you saw just a minute ago, was to assume that a signal such as Y is received. But it was comprised of signals such as X and some noise. Okay. Now, if we apply discrete wavelet transformation, the ith coefficient of discrete wavelet transformation at level M can be modeled according to the second equation. And as we know, wavelets are linear operators. So what we are going to do is that we are going to do a stochastic linear regression in here. This is called a stochastic linear regression, and we call that linear regression volatility in here, related to the volatility at ith instance multiplied by some IID Gaussian noise. So the volatility is modeled according to this equation. So by having the signal received and applying the wavelet transformation, now what we are going to do is to do some maximum a posteriori estimation in order to derive back the non-noisy signal, which was X at level, the ith coefficient of the wavelet transformation. So by having the hat X, then we can obtain all of the coefficients and do the inverse discrete wavelet transformation and obtain the signal, which is called denoising in this case. This is one application of one-dimensional denoising of a signal. But through the manipulations that are involved in the GARCH processes, xi, which is the ith coefficient of the discrete wavelet transformation, given this variance is normally distributed with this mean because of the linear regression, and the observation coefficient, the discrete wavelet transformation of the observation coefficient, is normally distributed with the variance of the noise, which was in the previous page. Now, the story with GARCH does not end for just very simple signals. Rather, it can be more complicated. Instead of having a simple signal in here, which is called the mean, we can assume that the signal in here itself is an autoregressive process. So this autoregressive process has its own coefficients called A sub k's, and then we assume again z of n according to the GARCH model, and we like to obtain not only the alphas and betas, also the coefficients of the AR process. By doing that, not only we have modeled the an AR process which is buried in noise, but also we have a new modeling which is called AR GARCH modeling, where AR process is of order R and GARCH process is order of PQ. In my talk today, I'm going to talk about general GARCH processes of order P and Q. But there are lots of work in various disciplines that they discuss that there is no need to go beyond order of 1, 1. It means that PB1 and QB1. So here is an application of what we just discussed. Let's assume that we have an observation Y, which is related to the right side, but the right side has some coefficients that are time varying, or stochastic coefficients rather. So this is somehow in some disciplines called time varying AR, time varying autoregressive process. And as you could see in the graph below, the PDF of the generated signal is the black. The histogram of the AR GARCH model follows the exact distribution, and the PDF of the best fitted Gaussian is far away. Of course, you could see it very clearly that in the main part of the PDF, the approximation is very good, but rather in the tail is very accurate, much more accurate. That has many applications in radar, sonar, and wireless communications. So now I would like to talk with you some terminologies that are used in GARCH modeling: heteroscedasticity versus homoscedasticity. Heteroscedasticity means time-varying variance. What it means is that if two processes such as y and x are dependent somehow, and we like to estimate, for instance, y by observing x, then this estimation, because it has a stochastic nature, it is not 100% accurate. Rather, there are some noises involved in the estimation. The variance of that estimation, which is obtained through a law called the Law of Total Variance, what you see in here, what you see in this equation is called the Law of Total Variance. That the variance of the prediction is time varying for stochastic time varying processes. Okay. But homoscedasticity is something that we all are familiar with, years of statistics, meaning that the variance is constant. So if I like to summarize what I just talked with you about, autoregressive or AR processes are the first equations, and an example of a GARCH process is time-varying AR, where you see that the coefficients of the AR process themselves are time-varying. For this case, this process is called non-stationary, meaning that its statistics are changing with time, such as mean, variances, and all other statistics of first or second order are time-varying themselves. Applications that time-varying AR found their ways in are enormous. There are many applications in engineering. For instance, in digital communication, OFDM gain estimation is done based on time-varying AR processes. In sonar, radar, and satellite communication, space-time adaptive processing, such as estimation of location and probably estimation of instantaneous frequency at the same time, is called adaptive space-time adaptive processing, can be done using time-varying AR. In image processing, image interpolation, we have few images at hand, but we like to interpolate between them. TVAR found its way in. In speech processes, interpolation of lost speech. For instance, someone was talking for a few minutes and some of the speech is lost, then TVAR can help to interpolate in between. In seismic processing, channel identification, for instance, obtaining the channel that is involved for a sound traveling from the surface of the earth to some depths in the earth, sometimes is done successfully using TVAR. Sleep apnea in biomedical signal processing also was based on successfully with TVAR. The coefficients that we just talked about in TVAR have different modelings. These are the three different modelings that are involved for the coefficients of TVAR. One of which was the very first example that we just talked about, that I showed the PDF of exact and the GARCH and the best fitted Gaussian. This was this example. The other example is that the TVAR coefficients themselves follow an AR process. This is the second one. The third one is the case that the TVAR coefficients, time-varying TVAR coefficients, themselves are based on some known functions, probably such as Chebyshev polynomials, Hermite polynomials, wavelets, which are enumerated in F. Now, what we had done, we had proven that the TVAR processes, given the past immediate information, result in heteroscedasticity. This means that all signals that I just talked about in seismic, in speech, in image processing, and other applications that I just talked about can follow what we just discussed so far. Because according to this theorem, all those applications have time-varying variances. For instance, the speech that you are hearing right now has time-varying variance. The variance of the speech changes with time. Okay. So in here, what we are going to do, we are going to provide you a very simple proof that a T-var process whose coefficients themselves are AR processes have not only conditional mean that is changing with time, also conditional variance that is changing with time. This means that, according to this very simple example, this means that a T-var process is a GARCH process. This is for the first time being proven. Oh, of course, with our collaboration with those people that I just talked about, and Professor Ritzi and Professor Arabshoy. So to summarize, conditional variance for real-time applications is not constant. And the other thing is that the conditional variances can be explained by the past conditional variances, meaning that conditional variances up to now are interdependent. Here is the example that we discussed at the very early slides. What you see here is the conditional variance of that process, that T-var order 1, whose coefficient was stochastic itself. You could see that the conditional variance is changing with time. And as a matter of fact, it is changing abruptly. That's very important in some branches of science dealing with jump processes. Now, I would like to talk with you some introductory material about denoising in general, how the denoising is done, and then we like to compare it to what we have done in this talk. Denoising in general, with today's denoising applications, based on wavelets, it assumes that you have a speech or you have an image that is comprised of this, according to this model, meaning that there is a exact speech or exact signal and then corrupted by some noise. Usually the noise is white noise, Gaussian modeled. And then what they do is that they apply a wavelet transformation. Wavelet transformation is a linear operation. It means that you multiply this signal, which could be an image or could be a speech, by this matrix. So accordingly, our model is also multiplied by the wavelets. And we know that the orthogonal wavelets have the following relationship, meaning that their columns are orthonormal. And because W is an orthogonal matrix, as a matter of fact, orthonormal matrix, the statistics of nu after being operated on by W does not change. So based on a Bayesian approach, we model this stochastic process, which was the original signal, speech or image or whatever, by a Gaussian mixture. So this allows us to apply the Bayesian approach through a map, maxima posteriori, to obtain the estimate of Q. The estimate of Q is obtained here, but according to these formulas, this is the model, meaning that there is a factor which is called shrinkage factor in applications, multiplied by the exact matrix. So from there, we can obtain the original signal, image or whatever. This is what I just discussed, is the wavelet approach to, more modern wavelet approach to denoising. But the more standard denoising based on wavelets are called hard or soft thresholding, meaning that they take the wavelet transformation of the image or the signal, and then they, according to the hard thresholding, they zero out some of the wavelet coefficients. And according to the soft thresholding, they modify the wavelet coefficients according to this formula, which is known. Okay. Now, what we had done is what you see in here, in the block diagram that you see in here, that we applied it to the Speckle denoising. What is a speckle? A speckle actually is a multiplicative noise, according to this model that you see, where an image, for instance, a SAR image, synthetic aperture radar image, is obtained, which is Y. But it is comprised of the exact image, which is not accessible, multiplied by a random process, which is basically do not know what the exact model for nu is. But modeling for the people that are working in this field are gamma or k distribution or log normal. And then what they do is that they take logarithm of y in order to make additive, to come up with an additive model. And then we apply the discrete wavelet transformation. From there on, discrete wavelet transformation and 2D GARCH modeling and all the rest is our novelties. So what we did is that, so what we did was that after taking the logarithm and then applying the two-dimensional discrete wavelet transformation at subband M. Subband, for all of you, as you know, is that some kind of filtering of order M, okay, concentrated at some frequency, let's say. So the bottom formula shows the subband M after the discrete wavelet transformation. And going through this 2D modeling of GARCH, so what we do here is that we have the wavelet coefficient, two-dimensional wavelet coefficients. These wavelet coefficients themselves are stochastic processes. So these stochastic processes are modeled according to a two-dimensional GARCH. And then after the two-dimensional GARCH modeling and map estimation, we denoise the wavelet two-dimensional wavelet coefficients, and then we do the inverse discrete wavelet transformation. So what we discussed a few slides back are summarized in this big square modeling by 2D. And then the inverse discrete wavelet transformation and exponentiation in order to inverse the logarithm, and then the denoised image is obtained. So what we see in here are real SAR images that you see in here, that we had done some filtering. I mean, a real SAR image was received by satellite, and then the denoising was performed, and we obtained that. And then you could see that the log transformed signal and also the discrete wavelet transformed signal in here. What we do in this figure is that we are going to show you the histogram of the exact signal, which is in blue, and the best Gaussian PDF to that. As you could see, the Gaussian approximation to this image is far away from the truth. And we did it for the log transform filter as well, and we can see that the Gaussian is far away from the histogram. But when we compare what 2D GARCH modeling after the denoising is doing, we could see that the 2D GARCH modeling very closely follows the exact two-dimensional process, as you could see in here. And it is more exact even in details, a lot more exact in details. So In order to explain multi-GARCH, which comes in slides later, I would like to discuss with you the simpler case, the 2D GARCH. We started with the 1D GARCH, which was the simple denoising, and then the 2D GARCH for the images. A 2D GARCH is a doubly stochastic process. Doubly stochastic process, why? And what you see in here is a double summation, and also in here double summation. And if you like, we can call this a two-dimensional RMA process, modeling and the time-varying variance of an image. Okay. So whatever you see in here is an extension of 1D GARCH. Again, we do linear regression, two-dimensional linear regression. Two-dimensional linear regression. And as we discussed in earlier slides, that we had conditionally normal for the observations given the volatility. So now our task is to obtain the coefficients of the volatility, which are the alphas and betas, and also to obtain the parameters that are involved in R. So we perform maximum likelihood estimation, log likelihood. We take the log likelihood of that PDF, and then we maximize this product, and we obtain all the parameters that are involved according to this formula. So the parameters that must be estimated are all alphas and all betas. As I mentioned earlier, the order of these summations at most are 1. At most are 1. And if this order was set to 0, we arrive at an approximation or a modeling called ARCH, Autoregressive Conditional Heteroscedasticity, where Professor Engel got a Nobel Prize for that in 1985. Here are some other examples, real examples. For instance, noisy signal and denoise signal. These are true signals. Some blood cells and denoised blood cells. You could see that there are some noises involved, but those noises are gone according to GARCH modeling. Some texture, you could see some texture here, but the noisy texture, but denoised in here. Again, ultrasound images being denoised in here. You could see that. So we saw one-dimensional wavelet, two-dimensional wavelets, now multi-dimensional wavelets. And why? Because some processes are a lot more complicated than two-dimensional. There are many signals that are more complicated than being modeled by a two-dimensional wavelets. For that, multi-wavelets have been offered, and multi-wavelets have all the advantages of wavelets, but even more because they are more exact, and also they can have some nice characteristics that are not shared by wavelets, basically being symmetric and orthogonal on a compact support simultaneously. This is not something that is shared by wavelets. So a multi-wavelet is this matrix that you could see here is comprised of these functions. That this matrix has the following property, meaning that the inner product is, meaning that the columns are orthonormal. And the dilation equation, it is called a dilation matrix equation, is obtained according to this. This is a very brief introduction to basic brief introduction to wavelets, multi-wavelets. And here is an example that the 1 and phi2 that follow the dilation equation, and their graphs are like Actually, multi-wavelets can be used on a signal such as Y in order to decompose it. This is the first decomposition and second level decomposition. Why we like to do that? We like to extract the relevant information out of a signal, out of an image, or out of a speech. That's the reason that multi-wavelets or filter bank, multi-dimensional filter banks are implemented. And by, as you could see in here, these signals themselves are correlated, and actually they are dependent. Therefore, in order to have a unified model for them, we like to introduce multivariate GARCH. What you see in here is that is an extension of one-dimensional or two-dimensional to m-dimensional. This is m-dimensional GARCH, meaning that it is not only an image, it could be more complicated than an image. And all the equations that we just saw follow exactly as we discussed, but to higher dimensions. These higher dimensions means that in order to have a conditional variance, which is time varying, we have conditional variance or covariance, which is time varying. Again, as we discussed about the two-dimensional and one-dimensional GARCH, we like to obtain the parameters of GARCH and parameters of the signal. This is done by maximum likelihood and maximum posteriori estimation, using the same analogies that we did for one-dimensional and two-dimensional GARCH. And the likelihood function is maximized, and theta, which is the vector of the parameters, is obtained. So I don't go through the exact details of these. So what we do afterwards, after we obtain the parameters of GARCH, what we like to do is to decompose the signal. One of the approaches to decompose the signal is fast ICA, independent component analysis, where the unknown correlation matrix of that multi-wavelet is obtained through fast ICA. And then by having the inverse of that, of course this is an estimate of that, it's not exact estimate of that, we obtain independent, we make the data almost independent. Therefore, after that, we can use the general denoising that we had discussed and extend it to more dimensions. But the details are, in terms of mathematics, are too complicated, and therefore I did not bring it in here for you. Let me just briefly discuss with you the fast ICA, because this is supposed to be also a class for some undergraduate students. Fast ICA is being used in source separation, and what it amounts to maximizing the non-Gaussianity, because all the signals, all man-made signals are non-Gaussian. I mean, speech, images, signals that are, wireless signals, all of these are non-Gaussian. Therefore, non-Gaussianity is an important criteria in order to decompose linearly or non-linearly combined signals into the its own components, which is called source separation. There are different approaches for source separations, one of which being high-order statistics based on bispectrum, the very original one, second-order statistics, approaches based on kurtosis defined as what you see here. Entropy and mutual information are also different approaches for source separations. An example is that the following, that we have some sources in here, some sources involved in S, which are linearly combined by A, so therefore this is a linear combination, but noise, it is observed in noise. It is observed in noise. What we have is X. What we like to obtain out of X is all S's that are in here, all S's. There is not one, there are many. So the easiest approach is to maximize the kurtoses, by applying some transformation to the observed matrix or signal, and then by maximizing that and obtaining these coefficients, weights, they are called weights, then by having the weights, we can apply the inverse of the weight matrix to X in order to obtain the sources. But fast ICA that we used in multi-GARCH is an efficient way of ICA, which maximizes non-Gaussianity according to this formula. So fast ICA that is used in mGARCH is based on this equation, okay? Where this f function, usually one of these are being used, and its effect, the decision based on which one to use is ease of operation. Okay, so if I like to discuss, if I like to summarize what I just discussed in this talk so far, is that one-dimensional GARCH, two-dimensional GARCH, multi-dimensional GARCH through multi-wavelets. But from now on, I would like to talk about the tracking approach using the same ideas. Why this is different? Because this involves more complicated modeling, which are called stochastic differential equations. Stochastic differential equations, whose parameters are themselves random processes or random variables. Therefore, the solution of the stochastic process itself is a random process. The paradigms in this modeling is based on Ito, the name of a scientist, mathematician, also Stratonovich. Both of these approaches are possible, and from one we can get the other. But our approach is based on Ito calculus. And how come Ito? Why stochastic calculus? Because tracking involves Brownian motion. Brownian motion, or the Wiener process, is nowhere differentiable. Nowhere differentiable. It can be proven that the variance is infinite. But the white noise is based on Brownian motion. And the derivative of Brownian motion or Wiener process does exist in all the tracking modeling. Okay. So a scientist named Singer introduced this equation for acceleration of a moving target. I would say target. Target could be an airplane, could be a robot, could be a submarine, could be a soccer player, many targets. So he introduced this equation for a target, okay? But we have shown that his model can be further extended by his own derivation. His derivation is based on the following assumptions: that if there are turns in the maneuvering, these turns, if they are slow, mu should be assumed to be 1/60. If there are evasive maneuvers, for example, for airplanes, right, this mu should be 1/20. And atmospheric turbulence, winds, these sort of things, the mu should be 1. This means that this function, very simple-looking function, cannot be something specific. It must be something stochastic. Because for different, how many slow turns, how many kinds of slow turns do we have? How many evasive maneuvering do we have? What variety of atmospheric turbulences does exist? Many things does exist. Therefore, this cannot be enumerated by these three simple cases. So what we did was that we assumed that that exponential itself is an stochastic process. You could see it in here. So this means what? This means first order time-varying AR. This means first order time-varying AR. But we proved that time-varying ARs are heteroscedastic. And if they are heteroscedastic, therefore they are the best application for GARCH modeling. Okay. But the thing about the tracking is that it involves not only the location of a target, but rather its derivatives. I mean, derivative of the location, speed, acceleration, all that. And if our measurements does have errors in location, therefore the derivative of the location would have impulses in it. Brownian motion, Wiener process, and even the acceleration is even more complicated. So according to our formulation, this tracking is best for, I mean, this tracking model, this modeling for tracking is best for real-time applications. And according to our theorem, acceleration is conditionally heteroscedastic. And we could see that the volatility, time-varying variance of acceleration, time-varying variance of the acceleration itself is conditioned upon the past. Okay. So now we invoke the Ito calculus. Why Ito calculus? Because the derivatives that are involved make impulses, creates impulses. Brownian motion, Wiener processes. So acceleration is modeled according to the Ito stochastic differential equation. And our goal is to estimate or to monitor a stochastic volatility of the acceleration. Okay. So the model of the acceleration would be according to this Ito calculus. This is us. This is our talk. But others have attempted this problem too. Histon and also three other persons, Berndorf, Nielsen, and Shepard, also attempted this problem. And we made the case that the Histon method makes, I mean, we proved it. We proved that Histon method makes the volatility to have a lower entropy. And lower entropy means that it is deterministic. It means that it is more deterministic. And that's not a good news. That's not a good news. Because among all the volatilities that exist, we cannot assume that limited amount of them can be modeled by the Histon method. And Berndorf-Shepard method is successful, but requires tremendous amount of computations. 5 minutes. Almost to the end. Okay. So I would like to just summarize this page by saying that GARCH modeling has the property of volatility clustering, meaning that large changes tend to follow large changes and small changes to follow small changes. And also it can follow the model the heavy-tailedness of the PDF, as I just stressed on that several times. And we use the AR GARCH model that we used earlier in the talk and invoke the GARCH conditions. These are GARCH conditions. For some of you that are interested in numerical computations, GARCH modeling falls in a domain of nonlinear optimization. Okay. So GARCH modeling provides volatility clustering. Large changes follow large changes, small changes tend to follow small changes. And also a property called black swan, meaning that it can capture sudden changes, jumps. It can capture jumps in any processes. And also it has heavy kurtosis, meaning that it is a super Gaussian, meaning that it has heavier tail than Gaussian distribution. So our proposed method is here, and the model for the tracking, is here. The model for the tracking is here. I don't think you can see the bottom level. What you see in here is bootstrapping. This one, I mean, the screen is, the resolution of the screen is here, the bootstrapping or resampling. This is very important for us because bootstrapping or boot sampling, resampling generates generates stochastically replicas of a stochastic process. So here I do a simulation for you that what you see, the blue and the red, are the accelerations. Jump. All of a sudden, see up to, for instance, 65 seconds, let's say 65 seconds, there is no acceleration in the y direction. And up to 100 seconds, let's say, there is no acceleration in the x direction. All of a sudden, there is an acceleration. 2 minutes. So we compare our approach with the existing IMM currently being used in many applications such as radar and sonar, used in multiple hypothesis testing and joint probabilistic data association filtering. So our simulation shows that the estimate of the acceleration, I mean time tracking of the acceleration improves by bootstrapping and to all GARCH modeling and the rest of the jobs. And here, do you remember, let me just go back. This was the exact acceleration in x and y direction. Now, what we did is in here. So you could see that the particle filtering, AR GARCH modeling, IMMs, and something called particle filtering alone. All of them failed. All of them failed to capture the acceleration of the target. But the only one that is successful, and to our eyes there is no difference, is the GARCH approach. So not only GARCH can capture stochastic behavior of signals in temporal domain, rather it can also capture the behavior of a signal in other domains, such as the ones that you see in the very last talk, applications in radar, sonar, or satellite tracking. I have concluded my talk. Thank you very much.
Okay, thank you very much, Hamid. Are there any questions? I have one. Where do you see applications of this where the volatility maybe could couple into other domains? For example, in underwater acoustics, we see that there are spiky or speckle-like behavior, but then when we see these long-tailed events or spiky events, we see increased Doppler spread and other type of things.
Of course.
Do you think there's applications where?
Of course, the last part, the very last part, can be extended with for general audience. The last part is state space modeling. So we can add another state to capture the Doppler as well in the modeling, and we track the instantaneous frequency by time. It is possible, but it would be a novelty over what we have done in here.
Okay, thank you very much.
Thank you very much. Thank you very much. Thank you.